Let me just finish the presentation, and then we can just open it up for the big harangue. Okay, so here I am on my mission to discover the pink virus. Let's talk about viruses first. A hot topic, wouldn't you say? You might like this as a review. Yeah, this is our friend swine flu right here, 2009 H1N1. So what are viruses? Packages of nucleic acid in a capsule or an envelope. The capsule is a protein shell. If they have an envelope, it is created as they emerge from the host cell. It's part of the membrane. The virus is either composed of DNA or RNA, but not both. They are unable to reproduce of themselves. They must use the machinery of a living cell called the host cell. They have no protein synthesizing system. They have no energy conversion system. They're incapable of movement. Okay, they just get blown and sneezed and wiped. They do not grow. Outside of the host, they're called virions. And here we have influenza virus. They're hijackers. They attach to the cell via receptors. Once inside the cell, they take over. They have genes that code for proteins that use the cellular machinery to do one thing only, really, and that is to replicate themselves. They can keep the cell alive, pumping out, more viral particles. Sometimes they will kill the cell so that they can infect the neighbors. This is what happens with the influenza viruses. And sometimes they can do both. They can stay inside the cell and turn it into a viral factory, and also insinuate themselves and trip transformational changes inside the host cell. RNA viruses come in a variety of types, the most sinister of which are the retroviruses. They carry an enzyme, reverse transcriptase, which allows them to make a DNA copy of their RNA genes. Now, why is this a great advantage? Because remember, the DNA in the host cell stays in the nucleus, right? But if you're an RNA retrovirus and you can make a DNA copy, you can get in the nucleus, you can get in the genome. When the DNA copy of the RNA gene sequences is inserted into the host genome, that is called proviral DNA. And I'm just saying it again, proviral DNA. So there's sort of a visual, graphic image of these strands of viral DNA. You can see very possible for it to become integrated into the genome. They do this essentially randomly. It's like lottery, like playing the lottery. When proviral DNA inserts itself into the host genome, it can be passed down to subsequent generations. These are referred to, when they're retroviruses, human endogenous retroviral sequences, HERVs. I don't know if you've heard of that. If you haven't, just sort of try and remember it, because it's going to come up again in years to come. The proviral DNA can be inserted into somatic cells, liver, kidney, skin, or into germ cells, sperm and egg. If they're inserted into somatic cells, like liver cells, if you're hepatitis C, you get into the hepatocyte. All of the subsequent generations of liver cells then contain this retrovirus, all right? Or whatever. If the retrovirus inserts itself into a germ cell, every cell in the body, all the somatic cells, will carry this mutation. So now you have a situation where you have exogenous virions, those are the viruses that are out in the world, and endogenous proviral DNA sequences. And there's no law that says they can't meet together in the same cell. So you have a cell that has proviral sequences in the genome, and it bumps into, one of its relatives, who makes it into the cell as well. And they can recombine. And this is the most recent and most interesting example of recombination. This is H1N1, 2009. And you see we've got genes from North American birds and some human genes, European, Eurasian swine, and North American swine. And it has been and will continue to be something of a lottery win for influenza A. Viruses and cancer. The first virus associated with cancer was found in 1964 in Burkitt's lymphoma, and here it is, Epstein-Barr virus. Since then, at least 6 viruses have been shown to be related to cancer. Probably there are more. The most recent you're probably aware of is HPV associated with cervical cancer, right? Human papillomavirus. Recently, here was a really excellent review of viruses associated with cancer, and this researcher estimates that between 15 and 20% of all human cancers are related to viruses. So what do? They reprogram the cell, they control proliferation, differentiation, cell death, integrity of the genome, and they can interfere with the ability of your immune system to recognize them. Well, yeah, I mean, if they get into the genome, it's a great place to hide, huh? HPV associated with cervical cancer appears possibly to be an etiologic agent with oral cancers as well, and possibly a viral link to glioblastoma. Isn't this interesting? Because we see, increase in the incidence of these cancers like glioblastoma. If they're related to a virus, it begins to make a bit more sense why the incidence is going up.